says converted into nitroaniline. How do you do that? How do you go about solving a problem like that? What's the first thing you want to do? The very first thing.
Count the carbons.
Oh, the carbons. Yeah, okay, but the carbons obviously are naturally obvious. This doesn't involve changing the carbon count. That's pretty clear. But when you have aromatic substitution reactions, what's important? Yeah, so this is an orthoparadirector and this is a metadirector. So that's the first thing. Now, once you've done that, then which substituent has to be introduced last? The nitro. Okay. So right away you know that you're going to have the nitrate aniline, but you also know that aniline undergoes oxidation during nitration, right? Because nitric acid is an oxidant. And so if you try to do the direct nitration, that doesn't work. And so typically what you have to do is you have to treat this with acetic anhydride impurity, or acetyl chloride impurity, to form acetanilide, which now is somewhat resistant to oxidation, but it's still an orthoparadirector. At this point, you do the nitration reaction. You get the paranitro acetanilide, and then how do you go back to aniline from here? How do you remove that? You do that with aqueous, base, and heat. And so if this is just an amide, so you're doing an amide hydrolysis, and that gets you to the direct to the desired compound. Okay? Now, one thing I want you to notice is that the amino group and the nitro group are, of course, related. One is the oxidized form of the other, if you will. And you already know that in aromatic rings and in others, you can start with a nitro compound and reduce it in a number of ways back to the amine. Now, you also know that that anilines can be converted into what? Into diazonium species. And so you know that you can do nucleophilic radical aromatic substitution chemistry just by converting the aniline to the diazonium species. So a compound like this really allows you to functionalize the remaining carbon atoms of the ring selectively. You know that you can do alpha brominations here, or alpha electrophilic substitutions on the aniline, because this is activated. Once the nitro group is reduced and you have another aniline here, you do the same thing at the bottom of the ring. And so this would be kind of a versatile intermediate for synthesis. Now I bring this up because of something that happens all the time. That is, when I read a scientific journal sometimes, I think, gee, we just talked about that in class. And so let me show you something. Hope this comes on now. Sometimes I have to looks like it's stinky. Yeah, here we go. Okay, so you'll notice that, so this is a paper that just came out last month in one of the scientific journals that comes out of Germany. This is one of the best ones in the field. And it describes the synthesis of compounds of the type that you see in the structures here. And so, if I can see that, I can make this a little smaller. Okay, you guys can still see the structures good. Okay, so these compounds are of some interest for their optical properties. Something you may know is that there's been a kind of a revolution displays for television sets, computers, and whatnot. And also, you've noticed, or maybe you've taken it for granted by now, that nobody uses really flashlights or anything like that with a incandescent coil. All of it's gone to light-emitting diodes. Now, a lot of the compounds that are used in these displays, diodes, and so on, are organic molecules, and they're aromatic organic molecules. So these compounds are being proposed because of their optical properties. Now, a random synthesis of a compound like this is not going to give you anything useful because, if you have a central benzene ring right there, and then you have 6 substituents surrounding it, unless those 6 substituents are introduced in the right order, you're going to end up with a god-awful mix. And so one of the compounds, or 2, may be of interest, but the others are going to be useless. And so you have to find a way to specifically make these compounds. Now, what typically you want is you want an aromatic compound that has electron-releasing groups in one half of the molecule and the electron-donating ones in the other. That introduces polarization of high electron cloud. So here's how they did it. And the reason I bring this up is because you guys really know all the chemistry that you might need to understand this paper. So they have this on the left-hand side, and I can see kind of a color-coded scheme for the substitution patterns that they're able to make using their method. And they color-coded it just to make it easier visually to see. That's not what's important. What's important is on the right-hand side. So let's see if you guys can read that. Is that big enough to read, or does it need to be a little bigger? Let me make it a little bit bigger. And see if we can. Okay. So you'll notice that they start with paranitroaniline, and that's the structure in the top. The paranitroaniline, depending on which compound you want to make, is partitioned according to those 3 reaction schemes that follow. And the one on the left, they say, and I hope you can read this, says number 1, bromination. So bromination, of course, means you end up brominating ortho to the nitro, to the amino group. So you can get the dibromo aniline in the first step. And then it says Sandmeyer. What's a Sandmeyer reaction? We talked about that. Anybody? I showed it to you this morning, actually. It's the nitrosate, it's the diazonium ion reaction. So the Sandmeyer reactions form the diazonium ion, and then typically what we saw in class was the Sandmeyer reaction treated with cuprous cyanide to give the cyanobenzene, cuprous bromide to give the bromobenzene, and so on. It turns out Sandmeyer reactions can also be extended to palladium catalyzed cross couplings. Remember the palladium catalyzed cross coupling reactions we talked about, Suzuki and such? So you can do Suzuki reactions where instead of a halide, you have an aryldiazonium. The aryldiazoniums are more reactive than the halides, and so they work really well with palladium catalyzed cross couplings. And so that's the 3rd step. The Sandmeyer reaction is just the formation of the diazonium species, and then the 3rd step is palladium coupling. So that allows you either to introduce a single version of the 2nd aromatic ring, or if you look all the way to the right, you'll see 2 different aromatic rings, which means that you've done sequential brominations and Sandmeyer reactions. So the Sandmeyer gives you access to, in this case, they brominated, done you can't see this. So let's see if you can see the cursor. In this case, they've brominated at the ortho positions, and then they get the diazonium compound, and they produce the same aromatic ring in all three sites. But you don't have to do it that way. You can do it stepwise, where you brominate one at a time, do cross couplings here, then do a Sattenmeyer, then do a cross coupling. That gives you all three different groups, and then you can do it all again. And so this is, if you look at the far right, this is kind of the maximum diversity that you get. You get 5 different groups. The 2 groups at the bottom right and left are the same. Presumably those could have been altered too, but they didn't see a need to do that. Now, this is chemistry that we've talked about in class. The reason I bring this up is because you need to realize that if you were, say, to go on in chemistry, what you should have gotten out of this course would actually serve you quite well. This is a picture of what the fluorescent properties of these compounds look like. And so, in one sense, they've been successful because they actually do have the optical properties that they were looking for in this research. And so, whether or not these compounds now turn into some article of commerce or not, I don't know. But they have indicated the luminescent behavior of a selected bunch of compounds. Notice that in one part of the molecule you have, I hope you can see this, yeah, you can. So notice that in one part of the molecule you have an electron donating nitrogen, and then in this part of the molecule you have methane sulfonates, or methyl sulfones, pardon me. So these are electron withdrawing, so in all 4 trichloromethyls. And so, as I said, you have an electron donating part of the molecule, electron withdrawing, so the pi orbitals are polarized. And that's typically what you look for. Anyway, this was just a little aside that I wanted to bring to your attention, because sometimes in a class like this you wonder whether anything that you learn is actually applicable to something practical. The answer to that is yes, it is. Okay, so let's forget about Sandmeyer reactions and aromatic substitution. Get back to where we left off last time. Now, last time, remember, we talked about DNA alkylation, and we said that you have the possibility to form lesions in the DNA that will prevent it from replicating accurately. And one way to do that is by alkylating the DNA. It's not the only way, we'll see other ways too. And so remember I said that we have alkylating agents like methyl sulfate, where we have a methyl that's bonded to this boxed group, which is methyl sulfate, which is a weak base, therefore good leaving group. The other alkylating agents that we had shown were mesylate, methane sulfonate, and that's really not much different at all. This is just missing one oxygen atom. So that's methyl mesylate. This would be the leaving group. And then methyl fluorosulfonate, or fluorosulfate, pardon me, which is this stuff here. This was the stuff that I said was called magic methyl, and this is no longer commercially available. So this is a registered trademark. In all these cases, you're getting the same kind of chemistry. Nucleophile is attacking a methyl group and displacing a good leaving group. Now, the nucleophile in this case is one of the amine bases in DNA, and so you can actually methylate the DNA not at one base, but at a number of bases, right? Because the DNA is a macromolecule. It has a very large molecular weight. And so you end up co-alkylating, say, a guanidine ring, and the methylation takes place at the oxygen atom. Now, once that happens, you end up disrupting the hydrogen bond that used to exist between these 2 atoms. And you still have 2 of the 3, but one of the hydrogen bonds is gone. So of course, the first thing you think of is, well, gee, okay, fine. So we lose one hydrogen bond. We have, hundreds of thousands of base pairs. What's the big deal? Loss of one hydrogen bond will do that? Well, no, because because this same reaction takes place at multiple G bases. And so it's not one hydrogen bond that you lose a whole bunch of them. I don't know at what point the structure of the DNA becomes unstable, but at some point it does, and it does not replicate. So this omethylation is just one way of performing a lesion on DNA. Another way of doing this is with an N-nitrosoamine, or in this case an N-nitrosourea. So these N-nitroso compounds, when they see acid, they do diazoniamine chemistry. And so you can figure out what the mechanism was for that reaction and see that what you end up with is methyl diazoniamine. This, of course, is completely unstable. Remember that aryl diazoniamines have some stability, although they are explosive. Alkyl, like this, alkyl diazoniamines react instantly with whatever nucleophile they find. And so this methylating agent also does the same kind of chemistry and disrupts the hydrogen bonding. Once that happens, then you have a problem, because either your repair enzymes come in and fix the damage, or you have a mutation. And most mutations are not good. Now, there are other ways to cause DNA lesions, and one of them is to go out in Hawaii sunlight. And so a reaction we'll talk about a little bit later on maybe is the reaction takes place between two thymine units. So if these are in close proximity in the DNA, then if ultraviolet light hits this, the double bond here and the double bond there form a cyclobutane ring. This turns out to be a radical type of a it's a photochemical reaction. It looks sort of like a radical process. And look at what you've done. Now you've covalently bonded. You form two carbon-carbon covalent bonds. This is a completely irreversible process. So there's really no easy way to go backwards. This whole piece of the DNA would have to be excised and destroyed. And so this is what happens when you go out in sunlight. Okay, so this is why people who live in tropical climates and who don't have a lot of skin pigment get skin cancer. So so this is another way to formulation. And finally, there are environmental toxins that will do this to you as well. So remember that polynuclear aromatic hydrocarbons, these are compounds where you have benzene refused to another benzene, and so on. These are compounds that are found in after combustion of carbon-containing fuels. So PNAs you get in diesel, you get them when you burn wood and so on. And typically what happens is the fully aromatic compound, this is oxidized, right? So the fully aromatic compound gets breathed in or gets ingested by you and me. And this compound is lipophilic before the oxygens are added. It's lipophilic, and so your body, in order to eliminate it, typically through urine, sends it to the liver, where it gets oxidized by a cytochrome P450. And so the cytochromes in the liver will oxidize one double bond as an epoxide, and this epoxydiol is usually the first thing that it forms. The other side of reactivity is here, by the way. So the next desired step is to hook up one of these hydroxy groups with a sugar, thereby adding the number of hydroxy groups to the whole molecule, and taking something that was formerly lipophilic, converting it into something that's now water-soluble or hydrophilic, so it can go through your kidneys and into the toilet. And so, but that process gets short-circuited. The way it gets short-circuited is that if this stuff comes into contact with the guanine base, this epoxide, this benzylic epoxide, is of course a very good electrophile. Why should this be electrophilic? Well, just imagine that the cation that you get is delocalized into these four rings. So epoxides in general are good electrophiles, but aryl epoxides are better electrophiles. electrophiles. And so you end up alkylating now, in this case, the nitrogen with this huge old piece. Now no hydrogen bonding takes place, and once again you've induced a lesion in the DNA that is going to cause a mutation. So you'll hear a lot more about this kind of process, I hope, when you take a biochemistry course or a biology course. So it's not my intention to steal their thunder, but I'd like to just kind of alert you to the fact that it's all organic chemistry. And so if you're going to understand biology these days, especially these days where everything is really migrated towards molecular biology, you really do have to have an understanding of chemistry, otherwise it's a black box. Okay, so let's kind of go over a little bit of what we heard in this chapter before going on to the last chapter in the semester. So the resonance energy of aromatic heterocycles is typically less than the resonance energy of benzene, and the minimum you kind of find at furan. So once you go to furan, you only have 16 kcals per mole, and that's reflected in the reactivity of furan, which reacts very often like a conjugated diene. Remember that furans do solar cycloaddition chemistry, just like the diene does, and they also do conjugate addition of, say, bromine, just the way butadiene does. And the reason that they do this chemistry is because, the reason that furans do this chemistry is because the loss in aromatic stabilization is fairly modest compared to something like benzene. It turns out that the protonation of pyrrolidine does not take place on nitrogen. And so this is something that I think always puzzles people. I think, well, it's an amine. It has an electron pair. Electron pairs on amines are basic. Why should this one be any different? The reason is because when you protonate on nitrogen, that electron pair is delocalized into the ring, so it's not strictly speaking on nitrogen. And so protonation on pyrroles takes place on carbon to give you a resonance stabilized cation. Notice that protonation on nitrogen does not result in any kind of resonance stabilization. Both processes result in loss of aromatic stabilization. One gives you a resonance stabilized cation, the other one does not. So that's something worth keeping in mind. Now, the reactions of the aromatic heterocycles in some way mirror the reactions that we saw for benzene, sort of our archetypical aromatic compound. And so you end up getting the familiar Friedel-Crafts reactions, but these are much more reactive species than benzene, and so the catalysis, the requirements for catalysis are more modest. You don't need powerful Lewis acids to catalyze this process. You can perform this process with anhydride and BF3 ether, and you get excellent yields. The site of reactivity, the first site of reactivity is at C2. And so you end up getting the acylation at C2, not at C3. The way we understand these positional selectivity issues is by considering always the resonance stabilization of the charged intermediate that results. And so Hammond's postulate again provides a guide for us. The relative reactivities towards electrophilic aromatic substitution are, and again, please don't memorize these numbers, that's not the purpose of this, but you need to know that pyrrole and furan and thiophene to a slightly lesser extent are all far more reactive towards electrophilic aromatic substitution than benzene. These represent relative rates for reaction. And so as a result of this far higher reactivity, you end up being able to do these reactions under mild conditions. As I indicated to you, this very high reactivity, especially for this compound, can be problematic because it has a tendency then to react with itself. In other words, the intermediate cation that you get ends up intercepting the pyrrole. The directing effects are understandable, once again, using it's the same trick that we did before, write the resonance structures for the charged intermediates. And so the heteroatom always will direct at these two positions. If you have an electron withdrawing group, it will direct here. And so in this particular molecule, the site that I'm pointing to is doubly, it's being directed, I mean, that's where both substituents, if you will, direct. And so you get exclusively one product. In this case, the nitro group directs 1, 3, there's 1, 3, so there, and the sulfur directs here, and so now we have sort of conflict, and you get a mixture of products. So nothing profound about this, it's just that you need to remember that you can rationalize these results by showing the charged intermediates. This is what I said about furan acting like a diene. It will do Diels-Alder cycle addition reactions. This is the diene that's a dienophile, or it will do conjugate additions, and these reactions take place with facility. Okay, now moving on to pyridine. Pyridine, as I said, the chemistry of pyridine seemed a bit idiosyncratic. It seemed as if it was unique to pyridine. That's true in one sense, but I hope I showed you that in the lectures that preceded. I hope I showed you that, in fact, you can understand pyridine chemistry through fundamental principles of reactivity. And so the electrophilic aromatic substitution reaction always takes place at C3. Now, how do you do that? How do you tell that electrophilic aromatic substitution of pyridine takes place preferentially at C3? Well, we show the 3 resonance structures, and then you compare those to electrophilic aromatic substitution at C2. At C2, you'll notice that you end up with one resonance structure that is a particularly bad one because it places a positive charge on an electronegative atom that does not have enough depth. And so these kinds of resonance structures typically don't contribute. So in essence, you have 2 resonance structures here, 3 there, and so that's why C3 is preferred. In order to get electrophilic substitution at C4, you end up going to the pyridine N-oxide, which should remind you a little bit of a phenol. I did not go through the resonance structures for substitution at C4 versus C3 for the pyridine N-oxide. That's something that I told you to do. It's in one of your problems. You can convince yourselves that the C4 substitution is favored over C3 in this case. And it turns out you can remove the oxygen, you can reduce this in a number of ways. So this allows you to selectively do reactions at either C3 or C4. At C2, the remaining position, we do this by nucleophilic substitution. This was a very strange reaction that had hydride as a leaving group. The red hydrogen departs with a negative charge, at least formally. This reaction takes place, in this case, with reasonable yield. The yields for this same kind of a process with a carbon nucleophile, which we also discussed, are usually a little bit more modest, but it's the same kind of chemistry. Now, you can perform the nucleophilic aromatic substitution much more easily on a 2-chloropyridine. And so recall that a 2-chloropyridine is structurally analogous to an acid chloride. And just as an acid chloride is more reactive than an aldehyde, so also the 2-chloropyridine is more reactive than pyridine. And I've highlighted the part of the structure that is homologous in both cases. So you have a way now of functionalizing any of the 3 positions of pyridine at will, and that turns out to be quite useful. Now, another way of doing all of this is through the pyridinium salts, although pyridinium salts give you a different product, that you can also activate this carbon-nitrogen bond towards nucleophilic attack in the normal way by putting a positive charge on the nitrogen. And if you do so, then these kinds of reactions take place quite easily. But, of course, here you don't end up with a pyridine, you end up with an N-methylamine. exploiting sort of the chameleon property of the N oxides. The N oxides are good partners for electrophilic aromatic substitution at C4, but they also participate in nucleophilic aromatic substitution. And so here, a dehydration of the conjugate acid of this gives you the pyridine back. So you have lots of ways of functionalizing the aromatic heterocycles. This is something you should kind of have anticipated, because the presence of a heteroatom in the aromatic ring gives you more diversity of the types of reactions that you can expect to see. And that, I think, is reflected in what we've discussed. Then the last thing we talked about, really last time, was the chemistry of vitamin B6, which is a cofactor. And these are all different forms of vitamin B6. Cofactors, remember what they are. They're small molecules that react in concert with an enzyme. So think of them as being the reagent that reacts with an enzyme. And so the pyridoxal does this rather nicely by exploiting the electrophilicity of this aldehyde, and then the pyridinium feature allows you to dump an electron pair into the ring, do some proton transfers, and then end up with a low energy pathway for a process that would be literally impossible to do certainly under physiological conditions. And so we went through one of the mechanisms, and I believe it was the decarboxylation. So an alpha amino acid can be converted into an amine by loss of CO2. Now, this is not a reaction that we've ever seen before. We've seen, as I indicated last time, we've seen the decarboxylation of beta-carbonyl carboxylates, where you have that pericyclic mechanism that spits out CO2 and gives you an enolate or an enol. You can't do that here, and so the way this works is by prior formation of this kind of an imine. So the amino acid forms an imine with the pyridoxal. Now, at this point, this electron pair that I've indicated with a negative charge can delocalize into the pyridinium ion, and you end up getting, this is overall neutral, right? You have negative and positive charge. Once you lose CO2, what's left is also neutral. And so that kind of tells you that the process is going to be fairly low in energy requirement, low in activation energy. And so this is what happens. If I push electrons, I end up with CO2 here. This is CO2. And I start with an imine, end up with an imine. And this imine is a neutral molecule. This is just the one of the resonance structures. This is the important resonance structure that's neutral. And so from here, you can see that all you need to do is move electrons back into the ring, and then just do a hydrolysis. So you end up protonating on this carbon atom. You can do that by delocalizing this electron pair, and you have the other amine hydrolyzed and so on. It looks a little bit complicated the first time you see this, but bear in mind that none of these steps are foreign to you. You've seen each and every one of these steps. And so what you need to do is you need to go back and work out the mechanism for the decarboxylation and for the transamination, which we talked about, but we didn't show the mechanism. And make sure you understand each and every one of the steps. And that's a very good drill for you to do. So, and then finally what we did was we segued to a discussion of nucleic acids, and we talked about the fact that you have this complementary hydrogen bonding that takes place between, at least in DNA, between an AT and a GC. And so these hydrogen bonds are one of the reasons why the two strands stay together. The other reason had to do with pi stacking of the bases, and we mentioned that too. So that kind of wraps up what I wanted to say for this chapter. And now that allows us to start the last discussion of the last chapter in the course. So let me first of all show you the reactions. kind of reaction we're going to be talking about. So imagine that you have a cycle of butene. Okay, now these compounds are strained, obviously, but you can make them. They're not unknown. And let's say that I have this particular isomer of cyclobutene, so dimethyl cyclobutene, okay? And now the cyclobutene is, as I said, strained, right? So if you heat this thing up, it shouldn't come as too big a surprise to you that the ring opens to relieve strain. And so if I just take this compound and heat it, and I don't have to heat it very hot, I forget what it is, but 100 degrees or less will do it, I'm pretty sure. Then what you get is you end up getting this E diene, okay? Okay, so what do we know about alkene stability? Which one is stable, the E or the Z? Other things being equal. The E, okay, so this gave us the most stable compound. So the first thing to think of when you read about this is that, well, we ended up, just getting thermodynamic control. But the problem with that is that with that argument is that I can perform the same kind of reaction on the other isomer. Okay, so now I have the other cyclobutene, the one with the two methyls. I do exactly the same thing here. I heat it up. And in this case, I end up with the EZ isomer. And what I don't see is I don't see that, and I don't see that. So there's no crossover. So you get, from this one, you only get E and E. From this one, you get EZ. Now, if I want to push arrows, I can push arrows here very nicely, right? Push arrows this way. And that accounts for the electron flow. But what does that not explain? It doesn't explain stereochemistry, because it doesn't tell you why one gives you one isomer and the other one gives you the other. That you don't get from just arrow pushing. So these kinds of reactions were observed, this one and many, many others that are related, were observed by chemists, starting in the late 19th century and into the 20th century. And for a long time, these were called, believe it or not, no mechanism reactions, because that just meant that we don't know what the mechanism is. And so people were really puzzled by this, because clearly something was going on. There had to be a reason, but no one really discerned that reason until fairly late. And the time that people started to understand this was in the 60s, the 1960s. And we'll talk a little bit about the history of that in a moment. So first of all, let's take a step back and recognize that the reaction that I showed you is the reverse of a cycloaddition. Okay, so it's it's the reverse of an electrocyclization. So these are reactions that take place between dienes, trienes, tetraenes, and whatnot, where the electrons rearrange, as I've shown here for this conjugated hexatriene, and give you a cyclohexadiene. Now, in this case, the reaction proceeds from the ring open to the ring closed species. Because why? Well, because there's no strain really, no appreciable strain in the ring. But the reaction could have gone in the other direction too, for all we knew, and the position of the equilibrium is going to be determined by the energetics of this versus that. So it's the same as any other equilibrium. But if you have, these are equilibrium processes, that the position of equilibrium is determined by the relative energies of the starting tilt versus product, same as ever. Now, there's no stereochemistry to guide us with the mechanism here. But the reason that this goes from, as I've shown, from left to right is because you've given up one pi bond and you've formed a sigma bond. Pi bonds are weaker than sigma bonds, and so, of course, it's going to go from left to right. The reason it doesn't do that with the four-membered ring is because of ring strain. So even though with there you give up, you would be giving up a pi bond or a sigma bond, you'd have to build a strained molecule, and so there it goes in the opposite direction. The Familiar-Diels-Alder reaction is in the same category of reactions, which are all called pericyclic reactions. That means around the ring. Okay, so electrons are moving around the ring, both cases. And sigmatropic reactions are maybe a little bit different. I've shown this trideutyrated compound, and I've highlighted one of the carbon-deuterium bonds. So think of this sigma bond, okay? I've pushed arrows for you, but imagine this deuterium migrating with the sigma bond from this carbon to that one. And that gives you this compound. So this is a sigmatropic reaction, which just means a migration of a, movement of a sigma bond. So all these reactions, electrocyclic, cycloaddition, sigmatropic, they're all pericyclic reactions, and they all can be understood in terms of orbital symmetry. So these are going to be these are reactions that are either heat activated or light activated, which means that you can make them go from starting to the product either by shining light on them or by heating them up. And the number of pi electrons involved, well, I should say electrons involved, because they don't all have to be pi electrons, is going to have a bearing on the stereochemistry, and as is whether it is heat or light activated. So these are the three things we're going to be thinking about. Heat or UV, how many electrons are we talking about, and what's the stereochemical outcome? Now, if you know two of these, you know the third one, any two. And so this was understood a long time ago. I mean, people kind of put this much together. They kind of knew that, well, okay, you get this many electrons, heat, you get this. They didn't know why. So let's see some examples. So this is the example I showed you. If I take this trans dimethylcyclobutene and I heat it, I end up with this compound. Now this is a 4 pi electron reaction. We always count electrons the ring open compound. Okay, so when we're talking about 4 pi, 6 pi, 8 pi, whatever, it's always the ring open, not the ring closed. And so in this case, 2, 4, 6 pi electron. If I heat this up, I end up with a cis product. If I shine light on it, trans. Now, this is quite peculiar. This is something we've not seen before, right? I mean, this is something that, is completely new. So, so the first thing you question is, gee, why do we need to know this stuff, right? I mean, does this stuff have any bearing on anything? The answer is yes, it does. Vitamin D is formed in your skin upon UV irradiation of a hexatriene. The stereochemistry of that reaction and the outcome, actually the chemical outcome, is determined by these rules. So yeah, it does have relevance to biology. That's just one example. Okay, now the rules that we're going to talk about, we're not going to go through it in excruciating detail, but these rules were articulated for the first time in 1965. And it doesn't mean that Woodward and Hoffman, and by the way, this is the same Woodward that the Woodward rules are named after, right? Remember when we talked about UV spectroscopy, we talked about Woodward rules, same guy. And Woodward and Hoffman wrote an important paper in 1965 that described these rules. They were not the first ones to think about this, but they were the first ones to put it all together in an organized way, along with Kenichi Fukui. And so these two people, Hoffman and Fukui, shared the 1981 Nobel Prize because Woodward had died a couple of years earlier. If Woodward had lived, he would have shared in that one. Woodward got the Nobel Prize a few years earlier in chemistry, so it would have been remarkable for the same guy to get two. But he certainly would have deserved it. Okay, so this would be a very good time for you guys to go review what you know about molecular orbitals. And so chapter 15, 1A, and so on. Yeah, it's funny how things keep coming back, isn't it? Yeah, I know. Yeah, I know. You know, it's, you think that it would be so nice. You just learn something, take the quiz, forget about it. Learn something else, take the quiz, forget about it. Wouldn't that be much better? Then you won't learn anything, right? Yeah. Okay. So let's take a look at butadiene. So I have 2 pi bonds. How many pi electrons do I have for butadiene? 4. Okay. So if I start out with 4 atomic orbitals, then I'll end up with 4 molecular orbitals. And these will be pi 1, pi 2, pi 3 star, pi 4 star. What's the star mean? Anti-bonding. Right, okay. So how do we determine the energies? Well, the energies are determined by the number of nodes. Node is what's defined as an area in space where there's 0 probability of finding an electron. And so in the lowest energy, pi 1, there are no nodes. In pi 2, the node is right here where I'm pointing. And that's where the polarity of the orbital changes. In pi 3, there are 2 nodes, here and there. In pi 4, there are 3 nodes, 1, 2, and 3. And so then you have energy levels, and you populate pi electrons in the lowest energy pi molecular orbital first, the second, and then you're out of electrons. This is the highest occupied molecular orbital. This is the lowest energy unoccupied molecular orbital. So we're going to be looking at the symmetries of these 2 orbitals, and especially this one. Now, the symmetry is determined by the end carbons. Okay, what happens at the end? So this is symmetrical, because you'll notice that whatever I have here looks the same there. But you'll notice that the symmetry here and there is opposite, so this is anti-symmetrical. And when you go to pi 3 star, this looks the same as that, that's symmetrical, and these are opposite, and that's anti-symmetrical. And now I'm going to give you a little shortcut. You don't really have to draw in all the orbitals. And the reason for that is because the lowest energy one is always going to be S, and it's going to go SA. Okay? It's important that you know this for some of the more complicated cases that we may discuss, but in most cases, all you need to remember is that pi 1 is symmetrical, and then it goes symmetrical, antisymmetrical, symmetrical, antisymmetrical, and so on. Now, the other thing you need to remember is that what we've shown for the pi system of butadiene applies equally for the pi system of any substituted butadiene with one proviso. The proviso is that none of those substituents better have pi molecular orbitals or non-bonding electrons that overlap with the butadiene orbitals. Okay? So as long as it's an alkyl and it doesn't overlap, no problem. Once it has pi electrons, then it's no longer butadiene, it's a different system. So what you're going to be looking at are the symmetries of frontier orbitals. Now, what are frontier orbitals? Well, these are the frontier orbitals, the HOMO and the LUMO. Okay, so what happens down here doesn't really concern us too much. It's what happens here that will determine the stereochemical outcome of these reactions. And so you analyze the stereochemistry of paracyclic reactions by looking at the symmetries of the frontier orbitals. Okay, so way back when, we discussed also the molecular orbitals of allylic cations, anions, and radicals. And because here we have 3 atoms that are sp2 hybridized, I have a pi1, pi2, and a pi3 star. And the number of electrons is going to be 2, 4, or 3, right? 2 electrons here plus 2, 2 plus 0, 2 plus 1. So no nodes, 1 node, 2 nodes. Now here the node coincides with the location of one of the nuclei. So at the central atom in P2, you don't have any electron density. And that is consistent with the resonance structures that we've always shown for these kinds of species. For the cation, you only have 2 electrons. So the cation, this is the HOMO, that's the LUMO. For the anion, this is the HOMO, that's the LUMO. For the radical, singly occupied molecular orbital, so it's a SOMO. We're not going to be looking at radicals.